Hello everyone. Let x of s be a Laplace transform of x of t. When x of s is expressed as a ratio of two polynomials, one in the numerator and another one in the denominator in the s domain, then the s domain representation x of s is called rational function of s. So the zeros and poles are two critical complex frequencies at which a rational function of a signal x of t takes two extreme values. Hello everyone. Let x of s be the Laplace transform of x of t, a time domain signal x of t. When x of s is expressed as a ratio of two polynomials in the s domain, then x of s will be called as a rational function of s. The zeros and poles are two critical complex frequencies at which a rational function of s takes two extreme values such as 0 and infinity. Let x of s is expressed as a ratio of two polynomials, say for example p of s by q of s, where p of s is b0 s power m plus b1 s power m minus 1 plus b2 s power m minus 2 etc. plus bm minus 1 s power 1 plus bm. And the denominator polynomial is a0 s power n plus a1 s power n minus 1 plus a2 s power n minus 2 etc. plus a n minus 1 s power 1 plus an. P of s is the numerator polynomial. This is called a numerator polynomial. Numerator polynomial of x of s. And q of s is called a denominator polynomial of x of s. Now let us scale this x of s by the numerator polynomial, especially the numerator polynomial by b0 and the denominator polynomial by a0. So what will happen? X of s is equal to, or let me consider like this, b0 is taken to be a factor, common factor outside, so s power m plus b1 by b0 s power m minus 1 plus b2 by b0 s power m minus 2 plus etc. bm minus 1 divided by b0 s plus bm divided by b0 divided by, if a0 is taken as a common factor then from the denominator polynomial, then the denominator polynomial will become s power n plus a1 divided by a0 s power n minus 1 plus a2 divided by a0 s power n minus 2 plus etc. an minus 1 divided by a0 plus an divided by a0. Yes. If the same function is represented such that the scaling factor is b0 by a0, it is called a scaling factor. Multiplied by a polynomial in factorized form in the numerator, s minus z1 multiplied by s minus z2 etc. s minus zm divided by, similarly the denominator polynomial is also written in terms of factorized representation, so s minus p2 s minus p1 multiplied by s minus p2 etc. s minus Pn. So the Z1, Z2, Z3, Z4, Z5, Zm, they are the roots of numerator polynomial. Roots of numerator polynomial. Similarly, P1, P2, P3, P4, Pn will be the roots of denominator polynomial. Denominator polynomial. So let me call those. What do you mean by roots? Let me introduce that. What do you mean by roots of numerator polynomial? Roots of numerator polynomial Z1, Z2, Z3, Zm will be called as a special, with a special name. They are zeros of X of S. Since S is a complex frequency, zeros can be defined as the value of the complex frequencies at which the signal becomes zero. You know that S, since S is a complex frequency, the zeros, what are those zeros represent? What do they represent? Zeros can be defined as values of complex frequencies at which the X of S becomes zero. Similarly, you can think about the roots of denominator polynomial of the signal or of the representation X of S. The value of S is equal to any one of the roots of the denominator polynomial P1, P2, P3, P4, Pn, then X of S will become infinity. So the roots of denominator polynomial, let me write it, roots of denominator polynomial. Roots of denominator polynomial, what are they? P1, P2, P3, P4, Pn are called poles. Poles of X of S. If S is equal to any one of those poles, P1, P2, P3, P4, Pn, then X of S becomes infinity, becomes infinite. So X of S attain infinite value at poles. At poles, I'll write it here. X of S, which is the Laplace transform of any signal X of t, attain infinite value at poles. Therefore, the region of convergence of this X of S does not include poles. An important point to be noted. I'll explain. Don't worry. One after the other, we'll explain. In a realizable system, the number of zeros will be lesser than the number of poles. What do you mean by that? The realizable system, number of zeros, Z1, Z2, Z3, Z4, how many roots of the numerator polynomial we have told? We have given about m number of roots. They are actually called as zeros of X of S. What is the meaning of it? If S is equal to any one of these roots of the numerator polynomial, then X of S becomes zero. Isn't it? Similarly, what are the roots of denominator polynomial? P1, P2, P3, P4, Pn. You can find out These are all called as poles of X surface. Normally in a realizable system, the number of zeros will be lesser than the number of poles. Also for every zero we can associate one pole in general, right? So we have a finite number of zeros, and the finite number of zeros will be lesser than the poles, right? So Z1, Z2, Z3, Z4, Z5, Z6, etc. zeros. So the plot of X of S is a three-dimensional plane plot, in fact. So we shall find out how to represent poles and zeros in S plane. What is S? S is actually a real component and an imaginary component. The real part of S is specified by sigma. Real part of S, and omega is equal to the imaginary part of S. What is S? S is called complex frequency. Complex frequency. So we shall see how to represent these poles and zeros. S is a complex plane where sigma will be on the real axis and omega will be taken on the imaginary axis. So in the S plane, this is called as S plane, isn't it? I have already told you that this is called as S plane. Any point on this plane will be a combination of sigma plus j omega. Sigma plus j omega. I have a function X of S is equal to S plus 3 multiplied by S plus 2, the whole divided by, it is S multiplied by S squared plus 6S plus 13. So let me find out what are the roots of the denominator polynomial and what are the roots of the numerator polynomial. The roots of numerator polynomial are all evident because Z1 is equal to minus 2 and Z2 is equal to, you know that it is minus 3. S plus 3 into S plus 2, roots of the numerator. Similarly, when you find out the roots of the denominator polynomial, especially you can find out that this is available in a quadratic format. So let us take this as an algebraic quadratic equation, and the roots of this equation, say for example, you can find out S is equal to minus b plus or minus square root of b square minus 4ac, 4 into 13, the whole divided by 2a, 2 into 1. So this will be simply minus 3 plus j2, or one of the other roots is minus 3 minus j2. There are two roots available, isn't it? S1 and S2, since it's a quadratic equation. Now one more part was also there. S was also there, isn't it? This is the root. These are the roots obtained only for the quadratic equation. As far as the next component is concerned, the root will be S is equal to 0. So the roots of the denominator polynomial will be P1 is equal to 0. First root in the denominator is 0. Second root in the denominator may be minus 3 plus j2, and the third root will be, the third root of the denominator polynomial will be minus 3 minus j2. You can find out. So the poles and zeros must be plotted on a graph sheet, isn't it? The graph sheet will have complex plane representation. So let us find out. One of those poles is actually, one of those poles is P1, P1 is equal to 0. The other pole is actually, say for example, the other pole is minus 3 plus 2j. So this comes here. The next pole will be, let me put it like this, in a cross mark, minus 3 plus 2j. Let me have 2j here, and similarly in the opposite direction, minus 2j here. So the poles are located, first pole with an int mark, second pole with an int mark, and the third pole with int mark. The pole, what are those poles? Poles will be, pole 1 is 0, the pole 2 is equal to minus 3 plus 2j, the third pole is minus 3 minus 2j. Those poles are plotted on the S-plane. Similarly, there are two zeros. What are those zeros? The first zero, you want to know what are those zeros? The zero number 1 is minus 2, zero number 2, second zero is zeros, minus 2, minus 3. So let me mark those values here. So let me encircle those poles with empty encircled points. There are two poles, sorry, 3 poles and 2 zeros. This is called pole 0 plot of rational function x of s, which had numerator polynomial and a denominator polynomial. So a squared plus, or let me put it in this way, what is the first function given? The numerator s plus 2 and s plus 3, whereas in the denominator we have s multiplied by s squared plus 6s plus 13. So roots of the denominator polynomial are represented as poles. The roots of the numerator polynomials are represented as zeros. Thank you.